Hello folks, today in this video, we're going to talk about momentum. We're going to both be able to determine the momentum of an object as well as to determine the impulse, which is the change in momentum for an object as well. So what is momentum? Well, you have probably heard about momentum a lot. It comes up so much in our vernacular language where you say, this football team has momentum or, that thing has a lot of momentum. We use it a lot, but in physics, there's a very specific definition that sometimes goes against what we actually think. Momentum is the product of an object's mass and its velocity. I like to say that momentum is mass in motion. So it accounts for both of those things because both of those things actually matter. If you get hit by a truck, you're going to want to know two things. You're going to want to know how big is the truck, because that matters, and well, how fast is the truck going? If the truck isn't going very fast, then you'll kind of skid off. And the same thing, if the truck has no mass, then it won't hurt you at all as well. So both of these things seem to matter when it comes to physical scenarios. So our equation for momentum, unfortunately, momentum, we ran out of letters for it. M obviously is mass. So momentum is given the letter P. So P is our unit, our letter for momentum, and P is equal to m times v because it's the product of mass and velocity. Now, because of that, it has some interesting units. The units of m, of course, are kilograms, and the units of v are meters per second. So that a kilogram meter per second is the unit of momentum. Okay, let's go ahead and take a look at a few things here. It says, which of the following has more momentum? A Mack truck sitting on the road or a small bullet fired at 1,200 meters per second? It must be the bullet. Even though the bullet is very small, it is actually moving since the truck... Man, I cannot write today. I apologize, guys. Since the truck isn't moving, it has a momentum of 0. Next question asks us, what's the momentum of a 0.4 kilogram baseball moving at 30 meters per second? Pretty easy enough. We know momentum is m times v. That's 0.4 kilograms times our velocity of 30 meters per second. And it looks like that ends up being 12. And then our unit again is kilogram meters per second. You can try the next one on your own if you'd like, see what you get. When I did this in my calculator, it looks like here it's 15 kilograms times 12 meters per second, and I got 180 kilogram meters per second. Okay, so that's how to calculate momentum, but obviously we want to actually do things with it. And one of the things that comes up all the time is the concept of impulse. So impulse, which is given the letter J, is the change in momentum for a particular object. So J is the change in momentum. The equation, of course, is pretty simple. If you're doing change in momentum in science, change we represent with a little delta there. So change is that, and then it, of course, is P for momentum. So change in momentum, that's my equation. Now, that's fine, but we can kind of make a better equation out of this. Anytime you see change in science, change always means final minus initial. So this is really final momentum minus initial momentum. And we could write momentum, of course, as mass times velocity, mvf for the final one minus mvi. I'm going to go ahead and finally make that a nice, neat equation for you. We're going to say that J, if I factor the m's out, is m times vf minus vi. And I find that while this is the equation on your reference table, J equals change of momentum, it's, I think, much easier to remember it as m times vf minus vi. So here it says, what's the impulse applied to a 980 kilogram car as it goes from rest to a velocity of 15? So we'll say J is going to be m times vf minus vi. Our mass is 980 kilograms. It goes from rest to 15. So 15 is the final. Rest is 0. That's the initial. And it looks like I get 14,700. And the units here are just the same because momentum is kilogram meters per second. So change in momentum is also kilogram meters per second. Now, impulse is useful because not only is it related to the change in momentum, but it's also related to forces. So we have another equation for impulse. Impulse is equal to force times time. Applying a force to an object causes it to change its momentum. And if you were to look at this kind of graphically, you see here that I've got, a force that goes up and then eventually goes down. Graphically, it's the area under a force versus time graph. So you could use that to figure out that impulse. So let's take a look here at what we like to call the impulse momentum theorem. Now, this equation is kind of on your reference table. Your reference table writes it kind of poorly. It says that J is F times T, and it's also equal to delta P. Well, I think a better way to write this, there's two equal signs. We don't need two equal signs there. We're going to go ahead and make that a little simpler because we already said that delta P is m times Vf minus Vi. So our impulse momentum theorem says that force times time, that's this part, equals our delta P, m times Vf minus Vi. So that is the impulse momentum theorem. It connects that force and time with change in velocity. So here we say a 0.1 kilogram egg is moving at 20 meters per second and is brought to rest in 1 second. What force is applied to stop the egg? So I want to find the force. I know the time is 1 second here. And then it's a 0.1 kilogram egg times Vf minus Vi. Now, Vf is going to be the 0 there. And Vi is 20 meters per second. So when I solve this out, 0.1 times this is -2, and divided by 1 is still -2, and that's going to be newtons because it's a force. Now, what does the negative mean? Well, you're trying to slow this object down, so you have to push backward on it. The force is opposite the motion here. So the negative is important. It tells us what direction that force is going. Remember that it is a vector. So in impulse momentum problems, you're going to want to be careful about direction. We're going to see some examples here. Now, these examples are all things with impulse momentum, that same equation. So if you want to give it a try, go for it and see if you get the same answers that I do. Otherwise, I'll walk you through some of these answers here. So this first one says, how long would it take to stop a 2,250 kilogram car moving 20 meters per second west if a force 80,450 newtons to the east were applied? So I'm going to go ahead. I know I'm going to need to use the force times time equals m times Vf minus Vi. You always know that if you're talking about like time and force and some momentum things here. So that's how I knew to use this equation. Then what I'm going to do is now plug in some numbers. Now the force is to the east and the car is moving to the west. I'm going to go ahead and say that west is going to be the positive direction. That means that this force to the east has to be negative because it is trying to slow the car down. So that times the time equals 2250 kilograms, my mass, times Vf. Well, Vf is going to be 0 because it wants to stop, minus 20 meters per second because that is the initial velocity. Okay, from there, just go ahead and solve for time. That's -20. Multiply that by 2250, divide by the 8450, and you get a time, it looks like, of 5.3 seconds. Okay, for this next one, very, very similar problem. Again, we're going to be doing F times T equals M Vf minus Vi. From here, what you would do, your force again is to the east, so I'm going to make that negative. Though, again, if you made the velocity negative, it wouldn't make any difference. I'm going to go ahead and use my car's mass as 1,500. Vf is 0 minus the 15 meters per second west. And when I do this one on my calculator, I end up getting 3.5 seconds. So try those in your calculator. Make sure you can solve that math and get the same answers that I can here. These next two are a little different. This one actually asks what the final speed of the car is. Now notice in this one, it's moving west, and you're applying a force to the west. So we're going to make west positive, and that means that both of those forces, both of those numbers will be positive. So when I do my equation here, I'm going to go ahead and say my force is positive 8450. That times the time, 1.5 seconds, equals 2250 kilograms times the Vf minus the 20 meters per second. Again, all positive here. When you solve this one out, I get a final velocity of 25.6 meters per second. Now, does that make sense? Yeah, because this car's moving west, and then we push it to the west. So it's going to have to go faster. Now, this next one says it's moving 50 meters per second to the west, and you're applying a force to the east, which means our car should slow down here. Again, I'm going to make west the positive direction. Same equation here. I know my force here is negative because it is in the opposite direction times the time. That equals my 1,500 kilograms times, I want to find VF, minus the original 15 meters per second. Solving that out, I end up getting a VF of 4.2. Oh, and sorry, I didn't put in the time. 2.5 seconds, 4.2 meters per second. Okay, folks, that is it with impulse and momentum. Thank you guys so much for watching. Have a great rest of your day.